This video is brought to you by mywayteaching.com.
So in this part, we are going to see about the musical pillars. Even in temples, often they have some pillars portraying human figures playing musical instruments, but seldom do these pillars themselves produce music. At the Nellapur temple in Tamil Nadu, gentle taps on a cluster of pillars carved out of a single piece of rock. It produces a basic notes of Indian classical music, that is Sarigamapa. The vibrations of these pillars depend on elasticity of the stone used and its density. So the vibration, it depends on these two qualities. It depends on the elasticity as well as its density. Musical pillars are categorized into three types usually. The first one we call it as Shruti pillar. As it can produce the basic notes, that is swaras. And the second one is Gana Tungal. Which generates the basic tunes that make up the ragas. And the third one is Laya, that produce tal when it is tapped. The pillars at the Tamil Nadu temple are a combination of Shruti and Laya types. Archaeologists date the Nellapayar temple to the 7th century, and it claim it was built by successive rulers of Pandyan dynasty. The musical pillars of this temple and even several other temples in the southern India, like those at Hampi, Kanyakumari, and even in the Tiruvananthapuram, are unique to the country, and they have no parallel in any other part of the world. They have the unique quality that they produce the musical ragas when it is tapped. Reflection of sound in an open pipe. See, when a high pressure pulse of air is traveling down an open pipe, it reaches the other end. Its momentum drags the air out into the open, where pressure falls rapidly to the atmospheric pressure. So, as a result, the air flowing after it in tube is pushed out. The low pressure at the end of the tube draws air from further up the tube, and the air gets drawn towards the open end, forcing the low pressure region to move upwards. So a pulse of high pressure air traveling down the tube turns into a pulse of low pressure air traveling up the tube. So here we can say that a pressure wave has been reflected at the open end with a change in phase of 180 degree. Standing waves in an open pipe organ like the flute is a result of this phenomenon. Okay, because of this phenomenon, these came into existence. See, you just compare this action when what happens when a pulse of high pressure air arrives at a closed air. It collides, and as a result it pushes the air back in the opposite direction. So here we can say that the pressure wave is reflected with no change in phase. In the first case, there was a phase difference of 180 degree, but in this case we can say that the pressure wave is reflected without any change in the phase. Now let us study about the Doppler effect. See, it is an everyday experience that the pitch of the whistle of a fast moving train, it decreases as it reaches away. Isn't it? That happens when we approach a stationary source of sound with high speed. Then the pitch of the sound it heard appears to be higher than that of source. As the observer recedes away from the source, the observed pitch becomes lower than that of the source. As we move away, it sounds like it's going, it's reducing. So this motion related frequency change, we call it as Doppler effect. Okay. We call it as Doppler effect. Okay. The Austrian physicist John Christian Doppler first proposed the effect in 1842. Bice Ballot in Holland tested it experimentally in 1845. Doppler effect is a wave phenomenon. It holds not only for sound waves but also for electromagnetic waves. So here we are considering only for sound waves, where we are not dealing with the electromagnetic waves. Okay. We can analyze the change in frequency under three different situations. Okay. First situation is observer is stationary but the source is moving. That is the first case. And the second one is observer is moving but the source is stationary. And the third case is both observer and source are moving. These are the three different cases that we are going to see. The situations 1 and 2 differ from each other because of the absence or presence of relative motion between the observer and the medium. See, most of the waves require a medium for their propagation. However, electromagnetic waves, they do not need any medium for propagation. They travel in vacuum. If there is no medium present, the Doppler shifts are same irrespective of whether the source moves or the observer moves, since there is no way of distinction between the two situations. Since first and two they differ because of the medium, there is a difference between the first one and the second case. So now considering the first case, that is source moving and observer stationary. Let us choose the convention to take the direction from the observer to the source as the positive direction of velocity. You just consider the source S, moving with velocity Vs, and an observer who is stationary in a frame in which the medium is also at rest. And let us consider the speed of wave of angular frequency W and the period T0, both measured by an observer at rest with respect to the medium. We assume that the observer has a detector that counts every time a wave crest reaches it. As you can see in this particular figure, at time t is equal to 0, the source is at point S1, isn't it? This is point S1, located at a distance L from the observer, and emits a crest. This reaches the observer at a time t1. That time t1 is equal to L by V. At a time t is equal to t0, the source has moved a distance that is given by Vs into t0. That is given, and it reaches the point S2, located at a distance L plus Vs into t0 from the observer. So at S2, the source emits a second crest. This reaches the observer at time t2. Okay. And we can write it as t2 is equal to t0 plus L plus Vs t0 by V. At the time n t0, the source emits its n plus 1th crest. So at the time, we can generalize this like this. So in a time interval that is given by n t0 plus L n Vs t0 by V minus L by V, the observer's detector counts n crust and the observer records the period of the wave as it is given by t is equal to n t0 plus L n Vs t0, the above equation, by n. If you take t0 common, this equation, we'll call it as A. It can be rewritten in terms of the frequency V0 that would be measured if the source and observer were stationary, and the frequency V observed when source is moving. So when we rewrite, we get V is equal to V0 1 plus Vs by V inverse. If Vs is very small compared to V, then we can, taking the binomial expansion to terms in first order, in Vs by V, we can neglect the higher power. Again, we can approximate this equation using the binomial approximation and neglecting the term which is negligible. It takes of this form. For a source approaching the observer, we replace Vs by minus Vs. Okay, in that case, V is equal to V naught 1 plus Vs by V. So the observer thus measures a lower frequency when the source recedes from him than he does when it is rest. He measures a higher frequency when the source approaches him. Okay.